Okay, hey, here we are on section 5.2. Welcome today. We are going to go through growth and decay and try to do this actually quite quickly. So I'm bringing it down to just a 1-day lesson rather than a 2-day lesson. And if I can get my mouse going, okay. Differential equations is the name of the game today. We're going to look at how can we separate equations and solve them. And then we also go into section 5.3 and do that even more so. There's also some growth and decay in here, half-life, population, compound interest that you may have seen before. So what exactly is a differential equation? A differential equation in x and y is an equation that involves x and y and derivatives of y. Previously, we've solved two types of differential equations, and we've had the y prime version, the dy dx version. We've worked with y double prime. Sometimes we had that initial conditions that we could find the c, but the strategy involved in solving these is to separate the variables. So this is called separation of variables, and a very important part to get this all off and running. So example number 1 is a nice problem. It says solve the differential equation, solve for y as a function of x. So that means I should have y equals and then blah, 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 blah in terms of x's. So I think what I'm going to do is rewrite this and write dy dx instead of the y prime. So I have 2x over y. Now, I want to separate my variables. So here's how I'm going to do that. Using a little bit of algebra skills, I'm going to multiply both sides by y, and that brings it up to brings it to the left side, and I have times dy dx equals 2x. Now, I want my variables to match up, so I've got y dy. I need to multiply by dx. So I'm going to have y dy equals 2x dx. Notice I kept that multiplier over on the right. I tend to do that because I know in the end I want this to be y equals, and why bring the 2 over as a 1/2 onto the left side when I'm going to have to move it back anyway. So that's why I do it that way. I'm going to integrate both sides. So my next step is going to be the integration step. And the integral of y, let's just make a boundary here. The integral of y would be 1/2 y squared. The integral of 2x would be 2x squared divided by 2 plus c. But we can see that those 2's are canceling, so I really just get x squared plus c, right? Now we want to keep solving. I want to solve for y, so I'm going to multiply both sides by 2 to get rid of the 1/2. So now I've got 2x squared plus 2c, but 2 times a constant, still just some constant, so I have a constant. I could call it c sub 1 for a different constant, but not necessary. The next step, I want to get rid of my squaring, so I'm going to go y equals plus or minus the square root of 2x squared plus c. And then that's kind of where I have to leave that answer. But notice it's y in terms of x's and c. This is called a general solution when we have that c. I'm going to just write notice the c. That's called a general solution. We've talked about that earlier in chapter 4, I believe. What if I gave you an initial condition like y of 1 equals -3? Now, I know that you're going to think I'm being stupid when I ask you to convert that function notation into an ordered pair. But you would be surprised by the number of people that screw it up and say -3, 1 as their xy location. So I would just, while you're taking and thinking about this statement, write it very clearly so that you have that ordered pair. Now we want to go through that ordered pair. So I'm going to take and go back to, actually I'm going to step back one step where I had that y squared. And I'm going to start off with that y squared equals 2x squared plus c. The next step I want to do is find c by using the by using that location 1, -3. It's like a slope field. We know our original function here must pass through the point 1, -3. So I'm trying to find the equation that has that characteristic. So I'm going to substitute 1, -3 in. So this will be -3 squared equals 2 times 1 squared plus c. 9 equals 2 plus c. Therefore, c is 7. And now I'm going to rewrite, remember doing these? Rewrite my answer or my equation. And that rewrite is going to look like y squared equals 2x squared plus 7. I replaced c. Now I want to solve for y. Y equals plus or minus the square root of 2x squared plus 7. Now, though, we can actually declare whether it's the positive square root or the negative square root. How? By looking at that initial pair. Notice when I plug in 1, whoops, that should be a 7. I need to get out a -3, don't I? Well, right now I have the square root of 9. The square root of 9 is just positive 3. So in order to get a negative, I am going to keep the negative case. That is how I determine which is the correct, which is the correct equation. So my final answer is going to be y equals negative square root 2x squared plus 7. All right, moving on. The proportional growth. This is a little bit about Algebra 2 and pre-calc stuff where we worked with proportionality constants. It says if y is directly proportional to t, then I know that as t increases, so should y. And I can write a direct equation, y is equal to k times t, directly proportional. If y is inversely proportional to t, then y equals k times 1 over t, or k divided by t. And that gives us an inverse relationship. So as t increases, y decreases. And that would be the case if you analyze what we wrote there. T being the denominator, if t rose and got larger, that's going to make a smaller number overall, so y would get smaller. Jointly proportional, this has to do with multiplication. So we're going to multiply a couple scenarios together. So this one says, if y is jointly proportional to x and 5 minus x, then y would equal k times x times 5 minus x. Okay, so that was just a quick review on what those words meant: proportional, direct proportionality, inverse, and jointly. So example 2 says a population of P increases at a rate proportional to the square root of the population. Proportionally, that is a direct one. So P increases at a rate proportional. Get a proportionality constant in there, like K. The square root of the population, so of P. It's kind of like I declared P as my population variable, so there it stays. If you want, go ahead and hit pause, walk through the rest of these, and then come back and see if you've got them right. Oh, actually, hold on. The next one changes, doesn't it? It says the rate of change of R. Ooh, how do I express a rate of change? A derivative. The rate of change of R with respect to time, so that immediately told me dr dt, is proportional, there's my k, proportionality constant, proportional to 33 minus R. Now, if you want to try the next one, go ahead. The rate of change of S with respect to W is inversely proportional. So ds dw is inversely proportional to 250 minus W. So that's going to place 250 minus W, the square root, in the bottom. Oh, what's with my square root? There's no square root. Sorry about that. How about just 250 minus K minus W? Letter D, the rate of change of U with respect to J is inversely proportional to the square root of U. Okay, so there's my is. This is my one side of the equation. This is the other side of the equation, right? So on this left side, the rate of change of U, that's a du then, differential U, change of U. With respect to J, so with respect to J, so du dj is equal to inversely proportional. That's going to push it to the bottom. Get my K constant in the numerator, square root of U, square root of U. And there we got it. So being able to read phrases and write them out so that we can go to the next step, often a skill you need on the AP exam. Example number 3, the rate of change of y is proportional to y. When t equals 0, y is 2. When t equals 2, y is 4. What's the value of y when t is equal to 3? All right, so I'd probably have to read that at least one more time. The rate of change, let me get a highlighter here. The rate of change of y is proportional to y. Okay, let's see if we can write that. The rate of change of y, dy, is proportional to, they don't really express what it's proportional to, so I'm going to make them both proportional to dt. The rate of change of y, so dy dt, is proportional to y, so I need a k times y. And then they want us to solve it when t is equal to 0, or when t is 0, y is 2. When t is 2, y is 4. I think what we're going to do is just go ahead and solve this without, get it into a y equals equation, and then we'll work with our variables. We'll talk about which ones to use when. So I'm going to separate my variables. And to separate my variables, it's going to be 1 over y dy is equal to k dt. I moved the y. I want to integrate both sides, so I'll come through and go 1 over y dy is equal to the integral of k dt. Well, k is like a multiplier, so keep that in mind. 1 over y, what's the integral of 1 over y? Oh, that's right. Natural log absolute value of y equals kt plus some constant. So k is just some multiplier. And then t, I need to bring on a variable. Now, to solve each side, I think I'm going to do this step before I solve for c. So I'm going to do this next step, and then I'll probably pause and find c. How do I get rid of a natural log so I can release y? Well, I put e as my base, don't I? Because e and natural log are inverse functions. That produces absolute value y for me, and I get e to the kt plus c. Okay, now this is a little bit of a tricky one. Yeah, let's go ahead and find that. I'm trying to decide whether I want to find c yet, but I think we'll travel one more step. E raised to this power is going to be positive, so I'm going to go ahead and release my absolute values. And remember, there's this, what do I want to call it? Exponent rule. 7 to the third times 7 to the second equals 7 to the 3 plus 2. Or a base raised to a power, base raised to the power equals e to the a plus b. That's an awful lot like what we have right now. So I can use my rules of exponents to work this backwards and say I have e to the kt times e to the c. But e to the c, e to some constant, is going to be just some new constant. I'm actually going to label it big capital C. Rearranging it, I get C times e to the kt. Interesting. Have you guys ever seen any formula that kind of looks like that? Maybe that formula? They're one and the same, aren't they? Just different variables. K instead of R for rate, C instead of P for principal. But it is our growth and decay model. So we just took a differential equation and solved it and found out that that is exponential growth decay model. That's kind of cool, I think. I always love that. All right, so when t is 0, I get out 2. I'm going to use that initial condition to find, let's find C with that. So I plug in 2 for y. I plug in 0 for t. So that gives me e to the k times 0. Well, e to the 0 becomes just 1. So I figure out that C has to be 2. Now that I know that, I'm going to erase our little exponent rules there. Now that I know that, I can replace C with 2. So I'm going to update my equation. This one has quite a few steps to it. Update my equation. I get y equals 2 e to the kt. Now I see why they gave me another ordered pair, another position on this exponential function. It's so I can find k. The other location was 2, 4. Now it's a good time to bring in 2, 4. So we are going to use 2, 4 to find k. All right, away we go. So 4 is my y, 2 times e to the k times 2, because it's a t, is the independent variable, which is 2. I can keep solving, so I'm going to divide by 2 and get 2 equals 2, or e to the k, e to the 2k. Natural log both sides to get rid of the e, divide by 2. So I'm going to have 1/2 natural log of 2 equals k. Or if you remember your log rules, that's a power rule that comes back, I could write this as natural log square root 2 equals my k value. So, grand finale, this equation is much like that, only our k is square root 2, isn't it? So I'm going to have y equals 2e to the square root 2t. And we're done. That was a lot of work. Now for a little bit easier work. In many applications, the rate of change of the variable y is directly proportional to the value of y itself. So really, the rate of change or the exponential decay model or growth model is really dependent on that value of y. How much material did I start with is what it's saying. And that makes sense because when we come through with our growth decay model, it is dependent on how much product is present. How much is in that seed? That really takes off, kind of shows us where we're at on our curve. Okay? So this is just explaining that. We know when k is positive, we're going to have growth. And when our k is less than 0, we have a decay situation. Now, it says the proof of the exponential model. If I were to solve this, it is identical to what I just solved, and we came out with that model. So I think saving time, let's not do that step. Oops, got a blank screen in there. I think I actually did that. Alrighty, so a little bit of application of growth and decay. Example 4, how long will it take an investment to double if it's invested at a 6% interest rate, compounding continuously? When it says compounding continuously, that means we are going to use the PERT formula, or our base is E with exponential growth. How long to double if we invested at a 6% compounded monthly? All right, so we need a couple formulas. Let's get those written down. Watch my time here, we're at 20 minutes. Okay, so the formula. Where's my formula? like I really need it. Y equals continuously compounding. We said that's the PERT formula, P e to the RT. Or if you would prefer, you could always stick with C e to the RT. Maybe sometimes you have seen it. Amount at the end is the amount that we started with, e to the KT. All of these are a derivation of the other. So they are just using different variables. Now, compounded interest formula, that is the amount I'll use is equal to the principal present 1 plus the rate expressed as a decimal divided by the number of compounding periods raised to the NT, the number of compounding periods we'd have. So if I have monthly, I'm going to have 12 times the amount of time we're talking about. Okay. Alrighty, what was the initial quantity C? How long will it take an investment to double if the investment's at 6%? How much to double? Well, they didn't really give us anything. That's a really big question mark, isn't it? Actually, let's just choose a number. We could choose 1,000, a million. I'm going to take it easy and I'm going to claim 1,000. I'm sorry, I'm not going to claim 1,000. I'm going to claim 1. So this is your choice. When it doubles, how much will I come out with? Well, I'll come out with a value of 2. So I just needed to double whatever it was I started with. All right, how long will it take it to invest at compounded continuously? 6% interest rate. We know that that gets expressed as 0.06 then. We want to find time. How long does it take? Our formula we know is Y equals P e to the RT. That means I want to start with $1, finish with $2 because I want to double e to the 0.06 t, and we'll solve for time. Divide by 1, and I get 2 equals e 0.06 t. Natural log both sides, I get natural log of 2 equals 0.06 t. To finish this, all we need to do is divide by, oh, sorry, that moved on me. Divide by 0.06, and we have the amount of time that would take. So I'm going to pause here a minute and grab, actually, I got it in my notes. That turns out to be a time of about 11.552 years. Remember, for the AP, you always have to express 3 decimal places. So there we go. I wonder how different this is going to be versus just compounding monthly. Curious. So let's go try and solve that little humdinger. I guess the little dollar bill guy is going to get squished down with my work. Okay, so next, part B. Let's do the question about compounding it monthly. So monthly indicates to me that my N value will be 12. My R is still 6% or 0.06. And I'm going to use the compounding formula. So I want to finish with $2 if I started with $1. 1 plus R is 0.06 divided by 12 compounding periods. That'll distribute that rate equally amongst all 12 months. And then the number of compounding periods would be 12 times some amount of years. All right. Solving this out, I would get 2 equals, I've done some of the math, so I'm going to have 1.015. That's the calculation of 1 plus that, raised to the 12t. Divide by 1.015. Okay, well, that's not a lot different than what we divided by before. We divided by 1 before. Equals 12. Hold it. I can't do that, guys. I need a natural log on this stuff, right? No, not yet. Okay. Yeah, we do. We certainly do. We got an exponent up here. All right, I need to natural log both sides. You're probably like, Miss Apple, make up your mind. Natural log, 1.015 raised to the 12t by the power rule. That will shift down in front, won't it? Power rule. And that's going to give me a natural log. My computer is slowing down. Natural log of 2 divided by natural log of 1.015. That's equal to 12t. So now we just need to divide by 12, don't we? And I'm going to just bring that down. All right, and then you'll be able to get the amount of time. I'm going to pause so I can tell you what that is. Okay, what you may have noticed is that I wrote this down wrong. This should have been a 0 there, because I was getting a really wacky answer. 0.06 divided by 12 was 0.005, and updating that, I come out with a time element of 11.581. So compare 12-month compounding to continuously compounding. Not a huge difference. A little bit. You knew it would be longer, but not a tremendous amount of difference. All right. The rule of 72 is a rule that talks about how long it'll take to double. And the rule of 72 is just a quick number that you can take 72 and divide it by your interest rate. So like that previous problem, we had 72 divided by 6%. And it would say, it's going to take about 12 years for it to double. Well, in our calculations, we came up with 11.55. So it's not really too inaccurate. Why 72? How did they come up with that number? Well, we know in order to double, we just had to divide by 2 and then we natural log both sides, right? If I check out what the natural log of 2 is, I'm going to put it in my calculator. Natural log of 2 turns out to be 0.693. So really a better number would be the rule of 69. A lot of people use the rule of 70. But then many people use it the rule of 72 because 72 has so many multipliers. So 4 goes into it, 6 goes into it, 8 goes into 72, 12 goes into 72, and an easy number to work with. So if you ever need to know how long it's going to take to double, just take your 72 and divide it by your rate. Okay, I'm going to pause this video and then finish this examples 5, 6, and 7 on another video.